My name is Erich Elsen, and I'm a research scientist at Baidu Research, which is located in Sunnyvale. And I'm here to talk to you about training recurrent neural networks at scale. Now, I hope everyone's been enjoying the conference. I always find it really interesting to see all the other work that everyone else is doing. It always makes me wish I had more time to work on everything. And I also know that currently we're a little bit behind, and I'm standing in between you and lunch. I'm going to try and make sure we get back on schedule. I'll do my best. So, thank you. There we go. So one of the things we're working on at our research lab is making interacting with computers as easy it is to interact with people. We believe that if we can do this, it could be as big a leap as it was to put a mini supercomputer in everyone's pocket. It could change our daily lives. And one of the things we need to do this is speech recognition, along with some other basic components. There are dialogue systems, which a lot of people are working on as chatbots these days. And there's also an interesting one in speech synthesis. It's interesting to me because in some ways it's a solved problem. We can all understand our phones when they talk to us, and yet it's not natural at all. No one wants to listen to their phone talk to them for half an hour. It's really grating if you listen to it for a while. So there's a lot of interesting work to do there as well. All right. So the system that we've developed is called deep speech because it's an entirely deep learning based approach to speech recognition. And it's being integrated into Baidu's products in China right now. And there's also an API available in the United States in both English and Mandarin. It's available to select partners right now. If you're interested, you should come find me after the talk. We announced a partnership with Peel last week, and they're using it in their remote control app, which has an install base of over 300 million users right now. So I'd like to get started by just talking briefly about how a deep neural network that's used for speech recognition might work. The basic idea is that audio is fed in and a minimal amount of digital signal processing might happen, so we might chop it up into a bunch of small spectrograms. And then we'll feed that into a recurrent neural network of some kind, which for the moment we can treat mostly as a black box. So you can make that up of a lot of different components. You can use vanilla RNNs or GRUs or LSTMs. You can do crazy things like residual and skip connections. There's a lot of different things you can do, but for the moment, let's just talk about what happens at the output. So at the output, what you're going to get is actually not exactly one letter at every single time step, even though that's what we sort of visualize. What actually happens is you get a sequence of probabilities over the letters in your alphabet. So in English, we might get a sequence of probabilities over the letters A through Z. But in Chinese or Mandarin, we're actually going to get a sequence of probabilities over 5,000 or more characters every time step. So then the problem becomes, how do we go from this sequence of probabilities and compare it to what we know is the right labeling? So if we know the right labeling for some audio file is the cat, but we end up with a long sequence of probabilities, how do we compare that sequence of probabilities to what we know is the right label and decide how right or wrong we were and how we can change our network to make it produce the correct output more often? So if you take a look at this sort of table right here, this is a very simplified view of what might happen. So in this case, the network can only output four symbols, the letters E, H, T, and a blank. And then there are 6 time steps going to the right. So you can see that the network has sort of output the. So there's a high probability of T for a while, followed by H and then E. But it's not exactly clear how we go from this sequence of numbers to something that corresponds to did it output the word the or not. And the basic idea that we use to figure this out is something called connectionist temporal classification, which is way too long to say all the time, so we just call it CTC. And it was a loss function developed by Jürgen Schmidhuber's group and Alex Graves in 2006. And the basic idea is that we look at consecutive letters, and when they appear right after each other, we just collapse them. So for example, we could write the word the in many different ways by repeating the T, the H, or the E. So we might have the, or the, or the, and they all collapse down to the in the end is the basic idea. So then we need to look at all the ways through this sequence of numbers that correspond to these labelings and essentially add them all up, and that will tell us sort of how much the network output the word the. Now this is actually a hard problem because there's many different paths that can be taken, and in this simple example it's not so bad, but in general you need to use dynamic programming to compute it efficiently. So on the next slide it gives you a slightly more realistic idea of, given a natural number of time steps and a slightly longer phrase, like how many possible paths there might be. So you really need to be able to compute this efficiently. And so this is something that we did at our lab. We wrote a very efficient implementation of this loss function that was, orders of magnitude faster than anything that was available in the open source world before this. And we released it under a very permissive license for the community to take advantage of. There's both a C and a torch interface, and both CPU and GPU implementations. So if you're at all interested in doing supervised sequence-to-sequence type of learning, then I encourage you to check it out and see if you can make use of it. So back to fundamentally deep learning for speech recognition. One of the advantages that we have over previous speech recognition approaches, so speech recognition has been around for a long time, is that we can scale with data. So previous approaches were done in an era where both compute and data were relatively limited, and they relied a lot on sort of hand-engineered features to try and extract useful information from the audio. And it actually works fairly well when you don't have that much data. It actually works better than our deep learning approaches a lot of times. The trouble that you run into is that as you keep adding data, you can't really take advantage of it. So those approaches, they sort of plateau and stop getting better. Whereas with deep learning, if we make our networks bigger, we can keep throwing more and more data at them and they keep getting better. Of course, that also means we need to do more and more computation to figure things out. But so here you can kind of see in this table, basically it's showing if we have 100% of our data and then 10% and then 1%, how the error rate scales. And you can see at 1%, which is only 120 hours of data in this table, we get over half the words wrong, which is actually pretty bad. Of course, I should point out that the test set we're using here is really noisy audio. This is like trying to listen to someone in like a loud bar or something. So this is not trying to understand me right now where these numbers are coming from. But getting over half the words wrong is still pretty bad. And then as we increase the amount of data to 10%, that drops to 23, and then to 100%, and it goes down to about 13.5. So in some ways, we've now reduced the problem of improving our error rates to simply one of collecting data and collecting the right kind of data, and then having the compute resources to actually be able to train on all of that data. So previous speech recognition approaches also often required aligning your label to the audio. So for example, if I was saying the cat, I might also have to figure out not that this one audio file corresponded to the words the cat, but I would also have to tell it where in the audio file those words were spoken. So from 0.6 to 0.8 seconds, I was saying, the vowel E and so on. And that takes a lot of time and effort to label. So with this deep learning approach, we actually don't need to do that alignment, which allows us to collect a lot more data more efficiently, which makes it much easier to train with lots of data. The other thing that's really nice is that it's actually fairly robust to labeling errors. So when you're collecting this much data, it's impossible to make sure that every single label is 100% correct. But we can do some experiments where we take data sets that are relatively small and have existed in the public for a while. So they've been really combed over, and the labeling rate for these smaller data sets really is close to 0. And then we can intentionally make them bad and see what happens. So we can literally take labels that we know are right and turn them into gobbledygook. we could literally say the label is gobbledygook, or we could just sort of smash on the keyboard essentially and just say the labeling is totally wrong, and then train our network with some percentage of the labels as garbage and see what happens. And it turns out that with somewhere below 1% of the labels being completely garbage, it hardly affects the networks at all. So this really gives us a lot of confidence that we can collect this much data and know that we have some small amount of errors in it, and it's not actually going to be a problem. So now, the other corollary of being able to collect all of this data is that we also need pretty large models to take advantage of it. If you try and use a smaller model and then just keep adding data, at some point the performance of that model is just going to stop getting better. The model just doesn't have enough capacity to take advantage of all the information you're giving it, and it can't quite learn how to generalize. So the easy solution, of course, is you just make your models bigger, which works, but then it takes even longer to train them, because now you have more data, and each time you evaluate your model, it takes even longer. So that turns out to be, quite a problem if we don't do something about it. One number we like to throw around is that training one of our models requires over 20 exaflops of computation, and it's really hard to know what that really means. An exaflop, 10 to the 18th, who really knows? If I was on a popular science program like Cosmos and I was doing my Neil deGrasse Tyson impression, I might tell you that that was 20 billion flops and hope that that somehow made it easier to understand, but probably it did nothing. I think the easiest way to understand what it really means is dollars. Everyone understands money, and it takes over $100 worth of electricity to train one of our models. So that's like maybe your power bill for the month at home, and every time we train a model, over the course of, say, 2 weeks, we're using that much power. So maybe that gives you an idea about how much effort it actually takes to train one of these models. Now, the fact that it can take 2 or more weeks to train a model is a problem, because as researchers, we'd like to think that we have a great idea and then we just need to implement it. Maybe we had a great idea in a bar and then we just implement it and it turns out to be perfect. Unfortunately, that doesn't happen to all of us all of the time, and we need to actually sort of do experiments and then learn from them and come up with better ideas and then go around this cycle a couple times, and at the end we'll have a great idea. So to do this efficiently, we'd like to make the experiment time as quick as we can, because we want to learn new things as fast as we can. And I really think this is one advantage that computer-based science has over wet lab science, is that our experiments often take much less time, so we can learn things much more quickly. Now, one solution might be just, well, use less data and make your network smaller, and then they'll go faster. You can train them faster, and you can learn from them, and then you can take what you've learned on those smaller experiments and just apply it at the large scale. Unfortunately, at least in our experience, findings on the smaller data sets with smaller networks don't translate to the larger data sets and the larger networks. And even worse is they don't always translate in the same way. So experiments that work at the small scale may not work at the large scale, and experiments that don't work at the small scale might work at the large scale. So there's really no information that we can gain by doing the small scale experiments, which is unfortunate. So this is just one example right here. So batch normalization is a very popular and widely used technique invented by Google a year and a half, 2 years ago. And it usually improves almost everything, as it does with most of our networks. But when we try it at the smallest scale, so our first experiment we tried on, I think, 80 hours of speech, a common data set called Wall Street Journal, in a relatively small network that only had one recurrent layer, it actually made things worse. And if we had never tried a larger network or a deeper network with more data, we never would have seen that this, in fact, was also a valuable technique for us. So that's just one example of why we think we always need to be doing our experiments at a relatively large scale. So given that we're always trying to do experiments at a very large scale, how can we make them go faster? So the obvious way is to parallelize across GPUs. And there are multiple ways that you can do that. You can use model parallelism or data parallelism, or combine them both. In our experience, we found that data parallelism is really the better one, at least at the scales we and everyone else are operating at right now. And when you're going data parallel, and we're using synchronous gradient descent and not an asynchronous version, it basically comes down to doing an MPI all-reduce type operation and doing it as efficiently as you can. So the scaling, the weak scaling that we get in our system is actually quite good. So going from 1 GPU to 8 is, so with 1 GPU we get about 55% of the peak flops of a GPU that's sustained across like a training run, so that's actually really quite high. And when we move to 8 GPUs, that drops to about 48%, which means we get about a 7x speed up, which is really quite good. And that scaling actually continues as we go even farther out across multiple nodes. The downside of doing this is that the mini batch size keeps getting bigger as we're adding more GPUs. And you know, deep learning experts in the audience might be getting a little frustrated when I just say, well, just keep making the mini batch size bigger, because it doesn't work forever. At some point, when you keep making the mini batch size bigger, your optimization stops working as well. So there is a limit. Now, to get that scaling on the previous slide, we actually had to implement our own all-reduce operation. So the one that comes in OpenMP out of the box is actually quite bad. And we were able to get about a 20 times speed up at smaller sizes, and even like a 4x speed up at very large number of nodes, just by writing our own. We're looking into making this available in general. We haven't quite figured out the right way to do that, but if you're interested in it, you should come talk to me and let me know. The more ammunition that we have that people want it, the more likely it is that we'll make it available. So we can't keep making the batch size bigger forever, which limits our weak scaling. And we're also limited in our strong scaling because the performance on an individual node unfortunately drops rather significantly as you make the batch size on that node smaller. So if you look at this curve, which is the performance of, say, a matrix multiply, as you start chopping the size on an individual GPU below about 32, performance really starts to go down, and that means our ability to scale is really hurt. So to scale well, we have to have a mini batch of about at least 32 per GPU, and the mini batch can only get so big, to maybe 1,024, which means that limits our scaling. So really quickly, since I'm about out of time, one technique we've taken to fix that is this persistent kernel idea, which is up on a blog on our site. Basically, the idea is we can store the matrix in registers, and then we can push the scaling limit down to a mini batch of 4 from 64, which enables much better strong scaling. I'll skip that. So basically, in conclusion, to get our speech recognition to work, we need to do experiments at a large scale, which really requires pushing the compute to the limit. And we're always excited to talk to people about how we can help them and share our knowledge about how to do this. So if you're interested, come find me after the talk. Thank you.